Today, I'm going to show you an AI called linear regression. This surprisingly simple model can make astounding predictions and is still widely used today. Before we dive in, let's imagine a problem. You're now an ice cream man and your business is thriving, but there's something that troubles you. You don't know how much ice cream you should buy for the upcoming days. Buy too low and risk a shortage. Buy too much, and you'll have to store the unsold ice cream. But what if we could write a program that would predict how much ice cream we need? That would be amazing, right? But how would we write such an algorithm? One way is to use certain known factors, like the average temperature, to infer the number of ice creams. This is because we expect higher temperatures to result in more ice cream sold. To create this program, we can leverage machine learning. In machine learning, the program learns to find patterns between the input and output data, like in our case with the temperature and ice creams. To train our program, we first need to collect a lot of data. We can then show this data to our program, and it will try its best to find the pattern. So every day, you whip out your notebook and write down how many ice creams you sold and the average temperature. After 100 days, you stop and plot this data on a graph. Each point represents one day, aka one measurement. The height of this point is the number of ice creams sold, and the distance from the left side is the average temperature. As you can see, there seems to be a strong relationship between these two variables. That confirms our hypothesis that higher temperatures result in more sales. On the other hand, if our graph looked like this, it would be a strong indicator that these two measurements have no relationship. In machine learning terminology, we would say that the number of ice creams is a dependent variable, as its value is affected by the temperature. The temperature is the exact opposite, an independent variable. That is because our sales don't affect the temperature. It's important to note that linear regression only works on data resembling a straight line, like the one with ice creams and temperatures. If our data looked curved, linear regression wouldn't fit the data very well. In machine learning, we say that linear regression can only capture linear relationships. Let's take a look at how this AI makes its predictions. Everything that linear regression does is calculate this simple equation. Y equals A times X plus B. Let me walk you through what each letter means. Y is the AI's prediction. X is the input, in our case, the average temperature. And A and B are what we call parameters. The job of our program is to learn what these two values should be, and it is also these two values that describe the input-output relationship. If we try to graph this function, everything becomes clear. You can see how changing the value of A causes the line to rotate and how changing B pushes it up and down. These two parameters are enough to create any straight line, meaning it can also fit the line we saw with our ice cream data. Of course, adjusting the parameters by hand and eyeballing the results won't give us an accurate model. Instead, we will create a program to do it for us. If we want our computer to do the heavy lifting, we must find a way to give it feedback. For example, you and I know this line fits the data better than this line. But your computer doesn't have eyes. Instead, we need a numerical measurement describing the prediction quality. Luckily for us, there is a simple way to do this. We can define this score by measuring how far is each point from the line. We can either average or sum these distances and then try to minimize this value. We call this measurement an error, but you also might hear people say cost or loss. The exact formula for this error calculation is called mean squared error, and it looks like this: y hat minus y squared. Y hat is the predicted value, and y is the correct answer. You might be wondering why we square the formula. The most prominent reason is to make all distances positive, otherwise they could cancel each other out. There are more reasons, but we'll leave those for future videos. After calculating the squared distances, we will average the values to get an idea of how off we are on average. We can do this by wrapping the formula with a sum and this term to turn the sum into an average. By the way, n is the number of data points we have. Great, we have an error function that tells us the quality of our AI, but we still don't know how to adjust the parameters to decrease the loss. To do that, we can use an algorithm called gradient descent. This algorithm is using partial derivatives to figure out how sensitive is the loss to small changes in A and B. Luckily for us, we don't have to know how to partially derive to use linear regression. All we need to remember are the two formulas, and we're good to go. The gradient descent formula for A is y hat minus y times x, and the formula for B is just y hat minus y. If you look more closely at the formulas, you will realize that these two parts are just the mean squared error without the exponent. We then subtract this formula from the parameters, and we also multiply it by the learning rate. What is a learning rate? You can think of it as a step size. The bigger the learning rate, the bigger change we will make to our parameters. That helps the AI gradually adopt new knowledge. Of course, there is a bit more to it, but that's the bare minimum you need to know. We usually set the learning rate to 0.01 or 0.001, but it depends on the problem. There's one last thing we need to cover. How do you know if your AI is well trained? We already have the loss, but it's hard to interpret. If I tell you my loss is 0.123, you can't really imagine what that means. A better approach for testing and comparing AI performance is called R-squared. R-squared is variance minus the mean squared error divided by variance. To calculate variance, we take the mean of all data points and plug it into our mean squared error formula instead of the prediction. That means calculating the average squared distance from the mean to each data point. One way to interpret R-squared is as a percentage. If you get 0.5 as your R-squared, you reduce the squared distances by 50% compared to the mean. Congratulations, you now know how linear regression works. If you want to, you can stick around and see how to code linear regression yourself. Also, consider subscribing to this channel to not miss future AI videos. For this demonstration, I'll use Python as my programming language, but you should be able to follow along in other languages. Note that many languages, including Python, already have libraries capable of linear regression. But today, we will be coding it from scratch. One last thing, you can find the source code and all other files on my GitHub. The link will be in the video description. Before we explore the code, let's run the program to see what it does. After running the main.py file, we get an error. That is because we haven't installed the required libraries yet. To do so, cd into the project folder and run the command pip install-r requirements.txt. After the installation is complete, we can run the file again. This time, you should see some numbers on your screen. That is the error of our AI, and as you can see, it is slowly decreasing as the model trains. Once the program finishes, a graph will be displayed, showing us the error over time. We can see that the error makes a sharp fall and then slowly descends into the minimum. Let's see how good the model is by running the test.py file. The first thing we see is R-squared, telling us that our model is 87% better than the mean. Once we press enter to continue, a graph will appear. The points are the training data you saw earlier, meaning that the x-axis is the temperature, and the y-axis is the amount of ice cream sold. Seems to me that our AI is working and fit the data pretty well. After we close the graph, we can enter our inputs and let the AI predict the outcome. This tool could be used by the ice cream man to predict his sales. Let's try to predict the amount of ice cream sold given the temperature of 33 degrees Celsius. Looks like we can expect 128 to 129 customers. The program will ask you for input over and over again, so if you want to exit, press Ctrl+C to interrupt the code. We'll look at how the training and testing process works under the hood. In main.py, we first import all the necessary modules and packages. In this part, we can configure the program. The number of epochs defines how many times will the AI go through the data. Higher numbers mean longer training. The learning rate is something we already discussed before. It sets the step size for the updates of the AI. Keep in mind that if you try to run the code and the error keeps increasing instead of decreasing, your learning rate is probably too high. The CSV path is the path to your CSV dataset. We're now using the ice cream dataset, but feel free to import your own datasets. The X column and Y column variables hold which columns of your database should be used as the input and output, respectively. Let's move on to the setup section. Here, we load the dataset using this function from the utils.py file. Inside, we can see that the function requires a file object and the X column and Y column we defined in the config. The function goes through every row of your dataset, converts the data to floating point numbers, and adds them to a list. That means we'll get a 2D array with every inner array holding the X and Y coordinates, while the outer array holds all data points. If we backtrack, the program also initializes both parameters to a random value between 0 and 1. In the training phase, the program repeatedly calls the step function until we run out of epochs. The step function takes parameters and the dataset as input and returns the updated parameters together with the loss, also known as the error. We track the loss by adding it to a list and also print it out for a quick review of the model's performance. Inside, the step function initializes the total gradient and the total error. The gradient is the derivative of the parameter, and we use it to update A and B. We go through each data point and get the AI's prediction as well as the error. We add the squared error to the total error and use the non-square one to derive A and B. After the loop is done, we turn the total gradient into the average gradient, and the same thing with the error. Meaning that we can now update the parameters by subtracting our gradient from them. Finally, we save both A and B to a file and plot the loss on a graph. Alright, training is done. Now let's see how we can test the AI. Once again, we import the required libraries and configure the dataset. We also check for the model.txt file. If it's not present, we can conclude that the user has not trained the AI. Knowing that the AI is trained, we will load both parameters and the dataset. We will now separate the input and output values. We can harness the power of Python and write these beautiful one-liners to get us the mean of the data, the variance, and the mean squared error. All of this together gives us R squared. Because our AI is just a line, we can calculate the ends and let the graphing library do the rest. To do that, we'll get the minimum and maximum inputs and calculate their corresponding predictions. Now we plot both the data and the line. And lastly, we will let the user predict the sales with his own input. And that's it. One last thing before I go. If you want to, there is a second dataset in the Datasets folder containing the information about the housing in Boston. You can read more about the dataset in the README file and fiddle around with it. I hope you liked this video. If so, smash that subscribe button so you don't miss my future AI videos. With that said, I'll see you in the next one.